It's a great honor to be back at HotChip's conference after 6 years. In light of current events, today I'm going to talk about the design philosophy of a interconnect network behind large-scale AI supernode, instead of talking about the engineering details of our actual product. So, as you know, supernode is becoming the norm for large AI data centers. Many companies are planning gigawatt AI data center right now. A supernode, it's not just a collection of loosely connected cluster of computers. Instead, a supernode tightly connects a large number of devices to form a single large computing system. The chip number that's involved varies from something like a typical AI server with 8 GPUs, growing up to hundreds of thousands of processors, up to perhaps 1 million processors in scale. And also, we are seeing that as you increase the number of processors in a supernode, the bandwidth per chip increases from 100 gigabit or maybe 400 gigabit per second to up to 10 terabit per second per node at the present time. Also, because of the computing devices are tightly coupled and requires a collaborative operation, the latency requirement per hop it's reduced from a few microseconds down to something like 150 nanosecond. Physically, the scale of a supernode it's going beyond a single rack and as large, expanding as large as the entire data center. Also, another important thing that's happening with the supernode technology is we are, in addition to the asynchronous DMA data copying across the process nodes, we are also seeing a strong demand for synchronous load store memory direct access operations. Another thing to be aware of is the type of devices connected inside a supernode goes from just connecting the GPUs and quickly expanding to a larger variety of devices such as a CPU, GPU, MPU, memory pool, SSD for storage, and a variety of intelligent NIC devices for connectivity to storage and other data center network. Also, the switch remains to be an important element inside a supernode. So, we are advocating for a unified common bus and networking protocol to connect the great variety of devices. Conventionally, you see a large number of protocols evolving in the domain of each type of the connectivity. So you see the alphabet soup down here. This is by no means the complete list. So of course, there were reasons for those protocol to exist. But here we are arguing for a unified protocol to connect all types of devices. And people would ask why. The first benefit is lower latency because of when you have a purpose agnostic protocol, any port of any device can be connected and also can also forward packets across the different ports of a given device without protocol conversion overhead. And secondly, as you know, in any given SoC, the SerDes channels is an important critical resource. So by removing the protocol-specific controllers from SerDes, any SerDes of any SoC could be utilized for all purposes instead of for a single purpose. Furthermore, we need a simplified schema, in particular the load store schema for memory access, remote memory access, in addition to the more conventional RDMA and also a unified remote procedural call to invoke functions remotely. Lastly, we still remain respectful of prevalent protocols such as Ethernet. So when we design the unified bus can natively run over Ethernet without further protocol conversion. So when we try to use a single protocol to connect both the local peripheral devices such as SSD and local memory pool, and when we try to extend such a local bus technology towards the data center scale, there are a number of challenges that we need to overcome. First of all, each node need to provide higher bandwidth in order to to achieve the data rate required for the different types of connectivity. Secondly, the physical link need to be longer reach because the network spans a physical space that could cover the entire floor of a data center, or maybe even up to the entire campus of data center. So this definitely exceeds the reach of an electrical cable. So the physical link have to go optical, especially for the longer reach links. And as we all know, the bit error rate of current optical link technology is much higher. It's about 2 or 3 orders of magnitude higher than those of electrical link. In order to run the protocol over a link with higher bit error rate, more sophisticated error recovery scheme is required, such as a link level retry and other things. Thirdly, the load store schema, which we have talked about earlier, requires the SoC design to be enhanced to be able to recover from link side error to prevent the processor pipeline from deadlocking due to perhaps a loss acknowledgement for a load operation. Lastly, I think because of the larger scale of the SuperNode system, we need to have put a lot of thoughts into providing the resiliency over failures of all kinds, both at the link level, node level, and rack level. So as we are talking about high bandwidth, low latency network covering a large scale, and we are also seeing that the bandwidth per node is seeing expansion from something like a couple of 100 gigabit per second to 10 or even more terabits of seconds. This is representing approximately 100x increase in network bandwidth. Then this begs the question on how to achieve a physical network with 100x increase in total bandwidth without incurring the 100 times increase in cost. Some considerations some thoughts need to be put into this problem in order to solve the cost issue. And we believe that this requires a new kind of physical topology, perhaps a hybrid of more conventional topology and other novel topology combined together to provide the necessary bandwidth required for the given workload, also maintaining the cost of interconnect at reasonable level. So in this diagram, I'm showing 3 kinds of perhaps topological elements. The first kind is a conventional Clos topology, which is versatile and trustworthy. And it also has the nice property of being fully symmetrical among the leaf nodes. We believe that the Clos remain to be a suitable topology for the top level network, perhaps spanning as many as a million nodes, but they need to be running at lower bandwidth because of the inhibitive cost required to build a Clos network. The second topology, which we will further expand in the later slides, is the n-dimensional mesh, which has the beautiful property of having high local bandwidth, and perhaps we can control a diminished amount of bandwidth for longer distance connectivities. So we believe that ND mesh is highly suitable for a single rack of up to tens of nodes and perhaps a large part as large as a few hundred to a few thousand nodes. Lastly, we are also seeing popularity of the ND sparse mesh, which is really a modified version of the second option here. The sparse mesh is suitable for a local deployment in larger scale, something like a few hundred nodes, because it's a switchless topology that provides a very high local bandwidth and perhaps a control amount of a longer distance bandwidth. And it also maintains a very, very low hop count corresponding to low latency. So this is suitable for smaller local deployment. So why do we believe a topology with a locality, perhaps a hierarchically localized bandwidth it's a reasonable design goal. I think compared to the conventional Clos kind of topology, there was in common practice there was less of a assumption about the locality of traffic pattern. So the table on the right side here shows that in typical AI training system, as well as in inference system, there are different kinds of parallelism scheme employed, and we can actually contain the higher bandwidth kind of parallelism domain at a local physical region, whereas as we go to the lower and lower bandwidth parallelism levels, those could be deployed at a physical topology, higher physical topology level that provides diminished bandwidth. So also you can see that the reduction of bandwidth demand at each level is either at 1 or 2 order of magnitude reduction. So this represents ample opportunity for bandwidth shrinking at a longer reach physical topology domain. And well, the n-dimensional full mesh topology, this is a conceptual diagram. Later on, I'm going to show you practical deployments of the kind of variants of this topology. But conceptually, you can visualize it as 1D, 2D, 3D, and multiple dimensions. Within each dimension, we have full connectivity across any node to any other node. But as you go from 1D to 2D, we provide another full mesh connectivity, but only pairwise across the corresponding nodes at the corresponding position. So the same idea could be further expanded from 2D to 3D and maybe even 4 dimension. So even though I'm showing the links at each dimension being the same color, it's totally possible to have links of different bandwidth, especially at the higher dimensions, corresponding to the locality of the nodes. For example, the first dimension should correspond to the highest or the most local highest bandwidth domain being the nodes at the same board. And perhaps the second dimension, you can either shrink or not shrink the bandwidth at the rack level, but definitely at the third dimension as you go from rack to either a large part or the entire room of the data center. At this tier, it's very practical to shrink these links to be a fraction of the bandwidth of the previous 2 dimensions. Now, let's just visualize the cost benefit. This is mainly due to the reduction in the fewer, perhaps no switch use to build the topology, and also the reduction of bandwidth as go from one dimension to the other, to the longer reach dimension. The shrinkage of bandwidth also correspond to the shrinkage of fewer optical modules required to build a physical network. So of course, the system cost here is a comparison with some assumptions in mind, but they are all normalized to the cost of a computing component. So as you increase the scale of the network, you can see that the cost of the network increase also. But this is not just increase, this is a superlinear increase in networking cost. So if we have a node of 10 terabit per second, one can see that the cost of interconnect can surpass that of the cost of computing components. This is the crossover point. Something like a few hundred nodes, maybe less than 500 nodes, the cost of interconnect can exceed those of the computing chips. But and the gap widens as you further increase the scale of the network. Now, once you change to this kind of UB mesh topology with perhaps 4x reduction of bandwidth per dimension, you can see that the cost curve of the interconnect remains to be much more flat. So at 4,000 node level, we are already seeing a 5x reduction compared to a symmetrical Clos topology. So here is a real-life example of how we build the product. So at the rack level, we are using this 2D mesh. So having the full mesh inside the board, but also having another dimension of full mesh across 8 boards, forming a system of 64 nodes. Also, we have some other sophisticated design to provide one backup node to increase the resiliency of the whole rack. So if using the rack as a building block, we can increase the size of the superpod or supernode by adding more racks. Up to 128 racks could be connected using a one-layer Clos topology between rack. And these single-layer Clos network give you the flexibility of scaling up to from 64 a single rack up to 8,000 node supernode, 8,000 chip supernode system. Now, here I'm going to talk a little bit about how to make the protocol resilient over optical link. As you know, optical link flickering or interruption is quite a high probability event. In fact, in real life system of a 512 node supernode, we are already seeing almost 3.5 flickerings per day. So if these processors are doing load store schema, any loss of a response from a load instruction can cause the pipeline of the processor to stall, resulting in a node failure. Now, we have to overcome the node failure to prevent the node failure from happening by a number of methods. First of all, we need to increase the resiliency of the optical link. So here, we actually introduce the two simple tricks to get much better resiliency. The first thing that's necessary is a link level retry. So suppose the transmission of a packet going across this optical module with 4 optical channels to another chip. Suppose a packet suffers from either optical module flickering or maybe a simple bit error. The packet will be marked as error or maybe not received by the other end. And the error recovery scheme will require the MAC level to retry transmission of that given affected packet. But if the MAC retransmits the packet over the same link that was suffering from a flickering, the flickering can last for quite a duration, up to tens of milliseconds. Of course, the retransmission will fail again if you route that retransmit packet on the same problematic link. Now, a nice enhancement is to retransmit the failed packet on an alternative link of the same optical module. Of course, because of this link, it's not suffering from flickering, the retransmission will be successful. Now, this is one kind of a common flickering problem that's seen in practical data centers. And then the second scheme can overcome a more serious failure in the optical module. So now if we pair up 2 MACs and 2 optical modules together and connect the links in a crossover fashion, as represented by the blue and red color lines here, any failure of optical module 1, the retransmission of packet will be routed to optical module number 2. So therefore, even in the event of the complete failure optical module, we can still guarantee that UB network is 0 packet lost. Now, this is representing about 100x increase and in the meantime MTBF. Just having that protection at the optical link level is not sufficient, because now we are talking about real-life systems of a few hundred thousand processors. So this is a very large scale system. Well, in the past, people maintain such systems by providing backup nodes. So connecting some backup nodes into the network, and also in the event of a backup switchover, there's a very tight time budget for repair. So we are seeing something like a repair, a failed node need to be repaired in as little as 1 hour time, just to ensure that second failure will not destroy the complete system. So how do we, as we increase the scale of the supernode, this kind of problem will become more severe. Now, how can we deal with a large-scale system-level resiliency? We are advocating for a hierarchical scheme. So earlier on, when we talk about the rack design with a 64 plus 1 rack, this one additional chip inside the rack provides additional resiliency at the rack level. So let's talk about how this is going to work. I'm showing a diagram of a working rack with 64 chips, all in green color, plus these are good online chips running the actual workload, plus one yellow color node chip of as the backup at the rack level. Now, of course, at the system level, we still have the rack level backup represented by these yellow box here. So suppose at the beginning, the green racks are running online services without failure. And after a while, one of the chip inside this kind of a rack suffers from a chip failure, and the system detects that. So declare this rack to be a failed rack. Know that you cannot do the backup because of the localized network topology. The backup, the high bandwidth domain need to be backup as the entire whole entity. So we deploy switchover from this fail node to this backup rack. Now, the service remains back to normal. And we take this fail rack offline. Now, here's the key. The offline node can be resumed because there's an additional chip here, which can replace the failed chip. Now, we can reconfigure the backup rack and to use the standby chip to replace the function of the failed chip. Now, this rack with a failed chip can be bring back online as the new backup or as an active node running less important service. Even though this rack is compromised, but it's still fully functional. This is almost like the spare tire in your vehicle, so that the car doesn't get stranded should the tire you have a broken tire. So, what is the benefit of this kind of hierarchical backup scheme? We believe that this the service time requirement of a million node SuperNode system, a million chip SuperNode system can be reduced from 1 hour. It can be extended from 1 hour to 1 month, or in other words, MTBF it's increased by over 100 times by introducing this clever scheme. So in summary, we introduce, we talk about the reasons for unifying the protocol and also the design philosophy behind the unified bus protocol. We also talk about novel and pragmatic topology design for a large-scale SuperNode system. We talk about the improvements of protocol design and optical module design. We talk about the system-level fault tolerance, and this is already enabling a SuperNode size scaling from the rack level of tens of nodes, and real life, we're already deploying somewhere between 32,000 to 1 million chips systems. So the day of super large SuperNode is already happening. So this should end the debate about super chip versus SuperNode. We believe that the answer should be super chip plus SuperNode. So in other words, on one hand, you make each chip as capable as possible, given the process technology limits, and at the same time, you increase the scale of the AI SuperNode system. Combined together or multiply together, these two factors will enable a gigawatt data center, AI data center to be built within the next couple of years. So for more details, you can look up the archive paper, which provides much more engineering details about the content here. Thank you.